Hello, welcome to my senior capstone project. So for my senior capstone, I just decided to create a new programming language which is called the W programming language. So for an introduction on why I chose this project, going back on all of the focuses on most programming languages, I realized that there are some problems regarding the simplicity, tooling, and efficiency of most modern day programming. So the main part with simplicity is mental complexity when writing software, especially regarding syntax and how you actually write code. The tooling, which is based on the correctness of a program and not introducing bugs into the code, which can take much more time to solve, as well as efficiency, where the underlying size of the program and the speed of it is very negligible, and so it will be slow. So I decided to create a programming language which would hopefully solve all three of these problems in one underlying system. So using the engineering design process, I looked at the problem and I saw that programming languages had a simplicity, safety, and efficiency problem. In doing research, I realized that a lot of these problems were caused by integer operations, which, for example, division and adding all those simple operations can lead to undefined behavior due to divided by zero or going above the integer limit. And so the requirements was that the solution needs to be robust but simple enough to use, and but they must also not harm performance than most other languages. That's a problem. Evaluating the problem, I realized that the issue stems from the implicit restrictions that integer operations have, and based on the type of data. You can't divide by zero, that's it, but you can divide by anything else. In our prototype, I created a language which uses what's called a type system, which keeps information. The compiler keeps information about what each type of data is being worked on, so that it can provide better tooling for the programmer and catch errors beforehand. And during the test, the current version of W, it turns the source into tokens, takes those tokens and parses it into an abstract syntax tree. It checks that syntax tree, and then it finally compiles it to C90 source. So the main changes that I did was minor syntax changes, both in the name of simplicity, but also to make sure that there wasn't any syntax ambiguities, which my original syntax had. There was also implement a few extra mechanisms, such as type refinement and type deduction. My W source in solution was that the W source can be verified, turned into proper C90 source that can be compiled anywhere else. And the process is completely done ahead of the program running, so it incurs no cost. And finally, for my communication, I created documentation and a breakdown video of the whole thing. The main challenges was the syntax redesign, which I had to fix due to the parser not having enough information to determine what the programmer intended for some certain cases. The C++ complexity, I realized that a lot of originally writing the language in C++, there was a lot of technical debt in the language, so I had to rewrite it, and I chose to rewrite it in Lua. The parser and checker were a bit broken for a while, but I was able to fix the logic regarding them. And finally, in the component integration, I couldn't turn it into an executable due to Mount Bethel computer restrictions, so I had to use a virtual machine instead. So here is a diagram of how the process of compiling a program in W works, where you have your original source, that's text, then gets put into the lexer, turns it into tokens, each with keywords, identifiers, and literals. Then it goes to the parser, which turns it into statements and expressions. Then this goes with the checker, which determines if all the types and whether these types, the logic of the program is correct. And finally, it goes to the compiler, which converts it back into C90 code. Here's a breakdown video. To help understand the problem that W tries to solve, we will look at a common example found in other programming languages. Here we have a simple function divide, which takes a left and right parameter, both integers, and returns the quotient of the two as another integer. So obviously, when we call this function with say 15 or 5, the result will be an integer 3. However, what happens if our right parameter is 0? Since division by zeros is undefined, the behavior of a program is also undefined. So how do traditional languages solve this? By adding extra logic to take care of invalid cases. For example, this is a function that exits if right is 0, avoiding undefined behavior. However, this comes at a cost. Here we have the machine assembly that our unsafe divide function generated, and here we have our checked divide function. As you can see, the checked divide function causes almost a 60% increase in instructions, both increasing program size and execution time. So how do we solve the problem of undefined behavior without relying on expensive runtime checks? Introducing W. Starting with the root of the problem, if we look at conventional type systems and programming languages, we see that there is some implicit range of values a type could hold. For example, an integer may hold a value between -128 to 127. Because of this, if we tried to do arithmetic that went above the range or broke the rules, we get an invalid result. So what happens if we represented types with explicit ranges instead? Here, we replace the types from non-obvious identifiers to explicit ranges, and now it becomes obvious that the result of our second expression is invalid. Returning to our divide function, if we substituted the parameter types for these ranges, we can also find control of what values are passed. Now that our right parameters type is defined to be -128 to -1 and 1 to 127, we can statically determine if a value such as 0 is invalid to use. Another problem that can be solved with the system is signed to unsigned conversion. Here, x is signed and y is unsigned, and so trying to find the sum of both would require an implicit conversion. However, this would give the wrong answer. Since we know the ranges of values x and y can be, we can determine if this conversion will be safe. However, the system does cause a problem with false positives. Here, this function will only divide value if it is not 0, so there is no threat of undefined behavior. However, how do we make sure this case is properly understood by the language? Here, we add a feature called type refinement, which refines the range of values a type represents under the predicate that guarantees it. So here, we know since the value will be 1 to 3 inside the if statement, it's still 0 to 3 outside, because we are checking if the value is not 0. But wait! It gets better. Since we know that the operation 50 divided by value is actually 50 divided by an integer 1 to 3, we can know that the result will either be 50, 25, or 16. And combined with our other return value of 1, we can know that the result of this function will either be 50, 25, 16, or 1, without needing any programmer annotations. So here, we can know that doing an operation such as dividing by the result of this function will also be safe. Now it should make sense of what W innovates from other programming languages. Thank you. So, based on my reflection, I built addressing the problem that the language ended up providing safety and correctness without sacrificing any performance, as was done all ahead of time. And asking whether I would do this again, yes, because I believe it was really fun, and I learned a lot about how most compilers for programming languages work. And what I did well was I did provide a good system providing with a type system in a language. What I could have done better was manage my resources better, not because of time, but rather because of the main sources I used beforehand. Where if I ended up using Lua all along, then I would have had more time to work on the features. And looking at my demo, so here is a little test where if I say something return 1, then it spits out C90 source code, which will do that. Or if I had a function which takes in an integer 1 to 3 and returns the number times 2, then I return calling that function. I could put 3 and it works. However, if I did this and I tried to pass in the number 4, it would say that I cannot call the function f with an improper type because it's open. Or if I tried to divide by 0, then it would say I can't divide by 0. Thank you.